So, good morning. I am Krishna Kumar from Krishna's classroom. Welcome to you all. Well, we continue from where we left last time. So, we were in fact looking at some interesting examples which paved the way for these kind of questions that we are going to ask. So, last time we defined what convergence is. In fact, point-wise convergence is the one that we talked about, and we have a sequence of functions. So let me some interval I of the real line or the whole real line, and with n equal to 1, 2. Suppose this is the sequence. Now, you know that for fixed x, say x equal to a belonging to I, f and a, the sequence f and a is a number sequence. I am taking fn from I to R. One can take it to C or even other fields, and depending on that is there, but we are now for the time being working on real valued functions. Therefore, that's why I use the word number sequence. Otherwise, it will be a sequence in the range. Right. Now we see that suppose limit n tending to infinity fn a exists. And we know what we mean by convergence of a sequence already. Therefore, in that sense, it exists, and we denote this number, whatever be the number. You know that it is going to be unique. The limit is unique. Therefore, with a, you associate with a number. If you want, let us call that fa. So fa is a number. Okay? It is uniquely determined. Therefore, now you run a over the whole of I. Suppose the limit exists for every a belonging to I. In that case, what happens? You have a function, and that function is denoted by f. So you have got a function f is defined by f of x equal to limit n tending to infinity f n x. This is how it is defined. Okay? Provided, of course, assume limit exists for every so we have the limiting function. So we say that fn converges to f. So simply if we say that fn converges to f, then it means limit n tending to infinity for every x belonging to f. This is what it is. Okay. That is the meaning of the statement. More precisely, this means this: for each x given epsilon positive, there exists an n which depends on epsilon and x such that modulus of less than epsilon for every n greater than this is the definition of convergence at the point x. Okay. So for each point, so the important point is that for each x, there exists an n which depends on x. Okay. Because here we have had this number sequence converging. Using that, we have talked about the convergence. We have found the limiting function under the assumption that it converges for all x. And then, of course, we are looking at the precise meaning of this. This is the meaning of this. Okay. So, for each x, this happens. Now, we were examining some examples. Now, we will continue with the process and then look at some more examples and see some of the problems that you normally encounter. Normally, we would like to have everything going smoothly, but it doesn't quite often. Okay. For example, the last example that we looked at was this was the example that we looked at. We defined n for x belonging to R and n equal to found that we looked at the series. So we looked at the series n equal to 0 to infinity fn x. We know that this is simple. The meaning of this is this. So this is the meaning of this. That means limit n tending to infinity sigma n equal to 0 to k equal to 0 to n fkx. This is a finite sum. It is well defined for each x. So there is no problem about that at all. Okay. Therefore, what we are asking is whether the limit exists. If the limit exists, then you call this, you denote this by this one. So this is the meaning of this. Okay. So what does it mean? See, this is some sequential sum, something like Sn x equal to sigma k equal to 0 to n fkx. This is Sn x. So you are asking whether limit n tending to infinity Sn x exists. This is the question that you are asking. If it does, then you say that is the sum of the series at that point. And now, as x varies over each point, you look at this. So you see, once again, it is sequential convergence that we are talking about. Something like that. Okay. Now what happens? So let us work on the given series. The given series is this. So if you look at the given series, then this is what it converges to. We have looked at, we know that fn0 equal to 0. Therefore, f0, which is the sum of this, this is equal to 0. Because every term is 0, so the sum is 0. When x is not equal to 0, we have seen that this is sigma x squared common so geometric series, and you can easily sum it because it converges. There is no problem about it because it is 1 upon 1 plus a positive number. Okay. So at the point 0 we have already accounted for, but at there it is taken care of by this x equal to 0. So each term is 0, so we have it as 0. But otherwise, this is what happens. So this converges. There is no problem because x is, if x not equal to 0, then this is greater than 1. The denominator is greater than 1. Okay. Therefore, the series converges, and this converges to, you can show that this is actually 1 plus ID due to 1 plus 1. Therefore, the function that you get is fx equal to 0 for x equal to 0 equal to 1 plus x square for x not equal to 0. And you can clearly see that the graph of the function is something like this. This is the 1. So this is the function that you have, and it is this point, the value of the function is 0. So this is the graph of the function, and you clearly see that f is not continuous. So we started with fairly nice functions, very smooth functions, but we found that it does not, the series does not converge to a continuous function. So one cannot assure that the properties that the sequence of functions do have is shared by the limiting function under usual convergence. For instance, a continuity that you have for each of these Sn's is readily available, but the limit function is not a continuous function. So continuity is not passed on under this limiting process. And there are many other properties. So here f is not continuous. So we look at another example. This is an interesting example. See, one thing I want to tell you is that mathematics grows out of examples. Okay? Therefore, never hesitate to examine an example. Examples are at the heart of the subject. It's not that theory came and then you give some example. Unfortunately, we teach in that line, but that is not the case. Okay? The actual process is that you keep examining examples and then find out certain difficulties or even certain niceties, and then we conceptualize a theorem from that and then try to prove it in all generality. So examples are very important because like in natural sciences, you know that the experiments or even the observations and the experimental results are very important in the forward pushing of the understanding of nature. Likewise in mathematics, see, clear-cut understanding of the examples. The examples provide you with the source of ideas. Okay, a very discerning eye can look at an example and read out a lot of things from that. So never hesitate to go for examples. One should keep examining examples because it's my advice to a student. Even before you have a theorem, and now in a general statement of a theorem, what are things will be there? There will be a certain set of conditions, or what is called the data, and then there is a conclusion. Okay, the data would consist of the premises on which the theorem stands, the special conditions that are attached to it, and then you say that under these circumstances the following result will occur. Or more abstract way, you write P implies Q. Q is your conclusion, P is your conditions. Now, even before trying to prove the theorem or trying to understand the proof of the theorem, you should start picking up examples. Take an example where the conditions P are satisfied and then examine whether Q is satisfied. Now, this is the direct analysis that you can do on an example. Sometimes the example you start with something very, very simple and then slowly increase in complexity so that you get a better understanding of the problem. Now, this is very important. Okay? So, having done that and got a feeling of things, you start asking more bold questions. What are the type of questions that you ask? See, your condition is something like this. P implies Q. I said P is this is the data. This is the conclusion. Now you ask how much the conclusion is based on this data, dependent on this data. What do? Slightly tamper with the data. Okay? That means construct examples where the data is not fully accounted for. And then you ask whether Q is still true. Okay? I give an example. Okay? So you take a closed bounded interval. Like 0, 1. Take a continuous function. Now, one of the results that you prove on this is that f is bounded. So this is interval, the closed interval 0, 1, which you know has two properties prominently. One is it's a bounded interval. It's a closed interval. Or in single term you say it's a compact interval. So if f is continuous on a compact interval, then f is bounded. Now, this is the statement that you make. This is a theorem that you make. Now suppose you start tampering with this. How do you mean by tampering with this? See, you have two conditions here. There are three conditions here. F is assumed to be continuous. F is assumed to be, the interval is assumed to be closed. The interval is assumed to be bounded. Okay? So you start tampering with it. What do? Remove the condition of boundedness from the interval. For instance, you ask whether the same theorem is true if you were to consider an interval as the half line but still you assume f is continuous. This is unbounded. You ask whether all continuous functions on this are bounded. Start looking at examples. Then you clearly see that fx equal to x is not bounded. Fx equal to x is not bounded on this interval. Therefore, you see that the boundedness of the interval seems to be very crucial. There cannot be something that you can completely throw away. Now, what about this is a closed interval? So let us start working on the open interval. 0. And still you assume f is continuous and f is, you ask whether you can conclude f is bounded. Okay? You would immediately see that, look at functions like this. 1 by fx equal to 1 by x on the interval 0, 1. You see that if you examine the graph of the function, it is something like this. Like this. You see that this is the interval that you are working with, 0 to 1. It's not bounded. It's not a bounded function, although it's continuous. Okay, so it's not a bounded function. So you cannot do away with closeness either. Okay, now you ask whether you keep the other things intact and break down on continuity. That's very simple. If you don't have the condition of continuity, then you see that on any interval you can define functions which are unbounded. Okay, so you see that how much this data is important for the calculation. If the data is still on a less stringent data, if you can prove this, then you get an improvement of this theorem. Okay, so that's just a analysis on the sidelines for the students to learn something about. Now let me go to the next example. The next example is set the sequence f of x equal to limit n tending to infinity of cos m factorial whole to the power 2n. Okay, so this is your m for m equal to 1, 2, 3, etc. Okay. Now this is defined for x belonging to R. Let us see what this function is. To get a feeling what you do, this is how you work on it. I am just, doing some giving some details mainly because for the students to learn how you work on it. This is how you do it. Look at f1x. What is f1x? f1x is equal to limit n tending to infinity cos m equal to 1, therefore this is cos pi x to the power 2n. Okay, what is cos pi x to the power 2n? Now you see that cos pi x equal to minus 1 or plus 1, plus or minus 1 for all integral values of x. Here, first cos pi equal to minus 1, cos 2 pi equal to 1, cos 3 pi equal to minus 1, alternately positive and negative, and therefore you are taking 2 to the power 2n. So when you square it, this minus sign will go, so it is at all integral values of x, this cos pi x square is equal to 1, and then when you take the power to n, it is again equal to 1. Therefore, this is equal to 1 for x x equal to x equal to k running from matrix. So at all integral values it is so. And when x is not equal to, what happens? You see that cos pi x, when x is not an integer, it is neither equal to plus 1 nor equal to minus 1. Okay? Therefore, you have it a something whose absolute value is less than 1, and then to the power 2n it becomes. Okay, so that's about f1. Now you start working with f2. With f2 what happens? So with f2 what happens? You see that the term that you are looking at is cos 2 factorial pi x. So cos 2 factorial pi x is cos 2 pi x. So you should have, this is equal to plus 1 or minus 1, plus or minus 1 when 2 pi the term that we look at is cos 2 factorial. Therefore, the important thing is this is 2 pi x. When 2 pi x equal to k or x equal to x equal to k by 2 or x equal to k by 2, you see that this term is either plus 1 or minus 1. You take the square of this and then to the power n. This is what you have. Therefore, this is plus 1 to the power n. So at all points k by 2, etc., the function takes the value 1. Everywhere else it is 0 for the same argument, because cos 2 factorial pi x, its absolute value is less than 1, and to the power n, to the power 2n, and as n tends to infinity goes to 0. Therefore, you see that the function is 1 at all these points. So you see the points, the number of points where the function becomes 1 increases. and eventually you can see the following. So this is the argument. So if m factorial x is an integer, then equal to, otherwise now let us examine where this is possible. Suppose x is equal to is a rational number. So x is equal to p by q. Now, for all m greater than q, what happens? Q factorial, sorry, m factorial, okay? If m is greater than q, now this is p by q, m factorial is the m factorial divided by q will be a integer. Okay? Therefore, you see that in that case, what you get is that limit mod f of x is equal to 0. Okay? Therefore, you see that the function becomes 1. Eventually, what happens is that limit m tending to infinity, limit n tending to infinity cos m factorial equal to 1 when x belongs to q and equal to 0 when x does not belong to. This is the argument. Therefore, the function has, the limiting function has a discontinuity at infinitely many points. Okay? Therefore, what can you say about this function? This function is not integral. This is not a Riemann integral. Even if you take on a bounded interval, it is not a Riemann integral. Although the limiting function is a bounded function, each of these functions, you look at each of these functions is a continuous function. Okay? Therefore, even the limiting function is not continuous. Limiting function is not Riemann integrable on closed bounded intervals. Okay? So you see that since it's a bounded function, or if you take any bounded interval, any of these functions is a continuous function, so it is Riemann integrable easily. So you see, Riemann integrability is also not carried through the limiting process. Continuity is also not something that is carried through the limiting process. So you see, you cannot simply work with expect the limits, the limiting function to inherit all the basic properties that the sequence of functions has. Okay. under usual convergence. Look at another example. As I said, you work with a lot of examples and get some feeling. Then you start searching for pieces. Look at this example. Now you know these are nice functions. Okay, continuous functions, smooth functions. And there is no problem with these functions. These oscillatory functions. Okay, and as n increases, the oscillation increases. And what happens is the square root of n also moderates it sitting below, because if the function is bounded by 1 by root n. So as n tends to infinity, what happens is fnx goes to 0. Why? Because we see that mod sin nx is sine and cosine functions are bounded by 1. Therefore, this is true. So as n tends to infinity, this goes to 0. So the limiting function is this. So you have fx defined as the limit n tending to infinity of 0. Now I said these are all smooth functions. Okay. Now you look at the derivative of this. F and derivative, each one is differentiable, and in fact differentiable as many times as you want. So the derivative is for each element. Now you can easily see that fn derivative at 0, if you evaluate, then this is going to be root n. So this diverges to, which diverges to infinity. So it doesn't converge. The derivative does not converge, so the derivative does not exist. In fact, there are several points where it doesn't exist. Okay. Therefore, on the other hand, you have fn 0 equal to 0. So you go to identically 0 function. So what is the limit? The limit of this is that this goes to identically 0 function, which is differentiable everywhere. The derivative is equal to 0. So if you look at this operation, d by dx of this is not equal to fnx. So the interchange of the property of differentiability with the limiting process is not valid. Okay. That's about differentiability. Here it is Riemann integrability. Again, continuity. Previous example also we have seen the continuity does not get carried through the limiting process. So next example. They're all interesting examples. I mean, it's these kind of examples which stirs up further questions. Okay, and from these questions, the mathematics grows. Okay, so mathematics is not a closed chapter. Okay, you start from a premises where you have reached, and then you see that there are some examples which again demands certain further knowledge. That's very interesting. So one should put your hand on examples. This is why I said you should learn to analyze examples. This is for interval. Now you see that for 0, for x equal to 0, what happens to this? Because of this function, you see that for x equal to 0, this function is anyway. Therefore, the limit is equal to 0. That's the limit. What about 0 less than x less than or equal to 1? We will examine this. And what happens to this? Now you see that this is not 0. See, this term 1 minus x square is strictly less than 1. Okay? And to the power n multiplied by n squared. So you see that n square 1 minus x square whole to the power n goes to 0 as n tends to infinity once you are confined to this interval. Okay? Right? This is a general exercise. See, there are two terms here. There is a term which goes to infinity. There is a term that goes to 0. So it's the product of these two terms. So what happens is, as n square goes up, 1 minus x square to the power n just pulls it down. And you see that this pulls it down to 0 more strongly than it pulls up to infinity. Therefore, eventually the limit is at every point the limit as n tends to infinity goes to 0. Therefore, you have what you get? The limiting function is equal to 0. That is what you call fx, which is defined as limit n tending to infinity everywhere it goes to identically 0 function. Now let us look at the term by term integration of this. So what is the integral of this? Calculate this. I leave it to you to calculate this. This is equal to integral 0 to 1 n square x 1 minus this is equal to this. You calculate in simple integration. This goes to plus infinity. Okay. that the limiting process and the integration over the interval 0, 1 cannot be interchanged. Or it is clear from this that limit n tending to infinity of integral 0 to 1 Okay, so once again, the interchangeability of limiting process and the integration is not valid in this example. So merely telling that a sequence of functions is convergent does not automatically allow the property of the function of the sequence of functions and the limiting process to be interchanged. So you cannot expect the same property to be true for the limiting function. Which is not that it is not always true, but there are many cases where it is true, but it is not universally valid. Okay, so we have seen enough properties, already examined enough properties which do not interchange with the limiting process easily. There are examples of that. So, one of the questions that you ask is the following: when can you assure that the interchangeability of the limiting process with the property of the function? Okay, obviously you see that the convergence criteria that we have introduced is possibly not strong enough to substantiate this. This is the problem. Okay? Merely that the function, the sequence of functions converge at every point and defines a limiting function is not possibly enough. Because if you just carefully look at what was going wrong, was probably at some points the continuous functions go to a discontinuous function. One of the first case that we looked at, then all these things give enough insight into what goes on. Therefore, we have to ask questions on convergence. Or what you say, you take back the concept of convergence to the drawing board and start looking at it very closely, whether you can do something on that. So that all these desirable interchange of the property with the convergence do work. Okay? So let us go back to the convergence. So what was the convergence? Once again, let us ask, say Fn on set I for each x which in turn means the following: given epsilon positive, there exists a n which depends on epsilon and x such that for every n greater than it's an integer. So this is the meaning of this. This is essentially the meaning of this statement. But the crucial point is that the n that you have would depend on x. That's what you can say, because you are talking about point-wise convergence. So at each point there is a corresponding n, and that n depends on x. Okay? Possibly this is the root of the problem. Okay? So you are seeing that a function which is a sequence of functions which is very smooth suddenly breaks down at all points. I mean, look at this example. Sorry, this is not this example, the earlier one that we have looked at, or any one of these examples. You see that something breaks down. For instance, in the study of continuity, you see that a function which is otherwise very smooth, a sequence of functions which are very smooth, in the limit breaks down to a discontinuous function. We have seen the other day the example of on the interval 0 to 1, the function x to the power n is polynomial function, and I have drawn the graph of this. This is the function. This is f1, this is f2, and f3, and so on. So you have got, say, f1, f2, f3, and so on, a sequence of functions, and so on. What happens? All these functions are very nice, smooth, and so on. But as you see in the graph, what happens is as n becomes larger, the function will start becoming steeper on this part and almost lying flat on this line. It is nearly 0 here. It becomes very close to 1 as x goes to 1. This is the nature of the function as n becomes large. So eventually what happens is as n tends to infinity, at this point the functions is even otherwise 1, therefore the limit is equal to 1. Everywhere else the function goes to 0. So you end up with a discontinuous function. Okay, it's clear? Right. Therefore, perfectly nice functions in the limit may go to a discontinuous function. Now this is one of the examples that we have looked at. Now what you can see is that the convergence becomes faster as you are closer to 0. The convergence is slower as you get close to 1. It's not at the same rate that the things are happening. As you go further and further to 1, see, the convergence rate becomes slower, which means given an epsilon, the n that you pick up for an x closer to 1 will be very, very high. Okay, your condition will be satisfied for a very large n. Whereas over here, it can be very small. Here for a small n, the condition will be. So that's a big problem. So if if you can control this, I mean, this is there is no control on this. That's the basic problem that you have. Therefore, if in the situation that you are considering, this is valid, when you can pick a universally valid number n, which is valid for all x, then possibly this kind of disaster won't happen. Okay? So let us try to modify this. Let us modify this. Given epsilon positive, there exists a n which depends on epsilon. Such that for every n greater than n, that means the same n works for all x. Whereas in this example, you have seen the same n does not work for all x. Okay. For instance, suppose you want to choose. So see, when x is not equal to 0, suppose you choose epsilon as the bandwidth is, so you want fn to be. So what happens is only up to this. See, everywhere the corresponding fn goes like this. So you see that there is some portion where it doesn't work. Your n would work only up to this. You can choose an n up to valid up to this. Beyond that, it won't work. Or you choose any n. There is always a point here for which this inequality won't be true. Okay. Once you fix an epsilon and fix an n. Okay, then you can always find a small n for which fnx minus fx is greater than epsilon, also in x, not necessarily all x. Okay, so this is the problem with this example. But if that problem is not there, then possibly our difficulties will vanish. Okay? So let us talk about it. Oh, yeah, at least some of the difficulties will vanish. Okay, so let me. Right, now this is the definition of this is called the uniform difference is that a n which is valid for all x on the interval exists, whereas in these examples that we have considered doesn't happen. That's the problem. Okay. Therefore, we ask the question: suppose you modify this and put a stringent condition. It's a stringent condition. Okay. More stronger condition that you are putting. Then you ask whether it converges or whether all these operations do work. Okay. So we say that a sequence Fn converges uniformly on I if given epsilon positive, there exists an n which obviously depends on epsilon, independent of such that this is the definition of uniform convergence. So under uniform convergence, lot of nice things do happen. Okay, right? So we'll have time to demonstrate one of these things. Maybe quote some theorems also. Now, first of all, see, to understand any phenomena is you get a feeling that well, everything I understood everything. Yes. But to get a real understanding or deeper understanding of this idea, I think we should look at counter examples. What you call counter examples. Counter examples are those where this does not happen. Okay, where it does not happen, then you have to really realize what is happening. Okay, so let us come back to our example. Give you one. We have already seen that limit for n equal to limit n tending to infinity equal to 0, x belonging to 1 is not included, this is equal to 1. That's the definition. That's fx. So fx is given by this one. It converges at all points. The question is, does it converge uniformly? Your experience with the graph tells you that possibly it doesn't. So and so on. These are the functions. So this is your f1, f2, and so on. This is your f1. Okay. Now let us try to devise a. Okay. Choose fix an epsilon. So this is your epsilon. Between minus epsilon and plus epsilon. It doesn't matter because here you are taking a non-negative function. Now, you want the graph of the function to be lying between the line y equal to epsilon and y equal to minus epsilon. Okay. Now you see that at this point, of course, the limiting function is equal to 1. Everywhere else, the limiting function is 0. right? Now you see that it converges to 0 everywhere, because you can certainly find a n for which it is true. Okay, but then you see that this doesn't happen uniformly in this case. So how do you show that it doesn't happen uniformly? So you have to prove the negation of this. What is the negation? The negation of this is this. Given epsilon positive, or you use this notation for every such that for every x belonging to I, and for every n greater than n epsilon, what is it? You have fx minus less than. So this is the symbolic way in which you write. Given epsilon positive, there exists n epsilon such that for a given x belonging to I, and for a given n greater than n epsilon, this is less than epsilon. This is how you see it. You want the negation. The negation of this is this. For a given epsilon, all these should be true. So if this is not true, then what happens? For some epsilon, this should be. Okay? So you take, there exists epsilon. So negation of this is, there exists an epsilon greater than 0, say epsilon 1. Okay, and for which, and for any n, for any n, for every n, there exists x belonging to I and n greater than n epsilon. So I call this x1. There is an n1 greater than n such that mod f of n1, say x1 minus f of x1 is greater than or equal to. This is the negation. Okay. For every epsilon is replaced by, there exists an epsilon, I denote it by epsilon. There exists an n is replaced by, for any n. Okay. So for any n, you can find a x belonging to I, x1. There exists an x belonging to I, say x1. There exists an n greater than this particular n, say n1, such that f of n1 x1 minus f of x1 is greater than or equal to epsilon. If this is true, then this is the negation. So So what we want to examine is, in this example, is this really true? Okay. So I want to find an epsilon. Suppose, let me choose the outside line. Suppose I choose epsilon. See, there is nothing in your thing where epsilon is small or anything. Epsilon is any real number. Okay. Suppose I choose epsilon greater than 1. Then what do you have? You have fnx minus fx is less than epsilon for every n greater than n epsilon. Are you convinced? Because this is your epsilon. So the value of f is either 0 or 1. In both the cases, you see that the difference between fnx and fx is certainly less than epsilon for every x. So that is not enough. See, this statement for uniform convergence is that it should be true for every choice of epsilon. So to negate it, essentially, it is not enough to just take an arbitrary epsilon and then prove it, but you have to demonstrate there is an epsilon. Now we see, suppose you choose epsilon to be, say, 1/3. I am choosing epsilon equal to 1/3. Okay, take a look. And this is important. I have slowed down here, trying to drive home how to analyze this kind of situations. So you choose epsilon 1/3. From your figure, what do you see? So this is your 1/3. Now all that you need to show is that there is an x1. If you choose any arbitrary n, then there is an x1 and there is an n1 greater than that, for which fn1 x1 minus fx1 is greater than or equal to 1/3. This is what we want to demonstrate. Okay. Now I will fix some epsilon. Choose any epsilon. Choose n equal to 1 million or something like that. Choose arbitrarily n. Okay, so we have chosen n. Now any n, suppose this is, now you choose an n1. See, for any n, okay, there is a portion of the interval on which fn x minus fx is greater than 1/3. See that? Fn x minus fx is greater than 1/3. Therefore, what you do? If you fix n, then you choose fix your n, then you choose 2n. Then you see that if you look at f2n is something like this, which always, therefore there exists an interval side to 1 on which is greater than. This is possible because what is this function? This function is psi to the power 2n. Want this to be greater than or equal to 1 by 2. This is what you want. Okay? You want to find a psi 1 such that this is true. And psi 1 lies between such a psi exists. Okay? Therefore, you see that this condition is not satisfied. You can always find some epsilon, say epsilon equal to 1/3, for which, for any capital N, you can choose N1 to be 2 or N small n to be equal to 2n, which is certainly greater than capital N, and an interval psi to 1 on which this condition is satisfied. Okay? Therefore, there is no uniform convergence. And now you ask a question. With uniform convergence, suppose Fn converges to F uniformly on an interval I, and Fn is continuous. What can you say about the limit? So the question that you ask is this. Uniformly to assume continuous on I for every n is F. The question. This is the question that we examine. So let us examine. Okay. So what you have to prove? See, you have to prove that limit t tends to x or you can even write this more precisely. So let us, what we want is, so this means that there is a, what about continuity? It is continuous at the point x, that's what we are saying. So f is continuous at x if given epsilon positive, there exists a delta such that mod t minus x less than delta. This is what it is. Okay? So what do we have to do? We have to estimate this. T minus x. Okay? what we are assuming is that f has come out of a sequence fn. F has come out of a sequence fn which converges to f uniform. So let us work on this. Okay. So we have to estimate this. So we estimate this. So given epsilon, can you find a delta? What we know is Fn is continuous and Fn converges uniform. There are two things that are. So we have Ft minus Fnt. Okay. Plus Fnt minus Fnx plus this is equal to, I have just interposed Fnt and Fnx, just added and subtracted. Now I can apply triangular inequality. Okay, where t and x belonging to the interval. Now you see that Fn converges to f uniformly. Therefore, given epsilon positive, there exists such that this is for every s belonging to this is true. That means if I choose my n, so I choose n to be equal to some n1 where n1 is greater than epsilon. Now what do I get? I get then mod Ft minus Fnt is less than epsilon by mod I am assured of this. Okay. Now for this particular value of n, so what I have is this. I have Fx. This inequality is true. Okay. Therefore, what do I do? I see that this is less than epsilon by 3. So this is less than or equal to now what do I do? I use the continuity of Fn1. Now n1 is fixed, I don't have to bother about any other n. Okay? So Fn1 is continuous. See, Fn1 is continuous. So what does this mean? This implies there exists a delta positive such that epsilon by 3 for every e comma x such that mod less than delta. So use this. Okay. Now I am working on Fn1. So I have the continuity and just use this. So given epsilon by 3, there exists a delta such that this is true. Therefore, what do you infer? Mod ft minus fx is less than epsilon for every t x such that mod okay. So if you examine this proof, you will see that it is the uniform convergence which allowed me to fix this otherwise it would not have been possible. Okay. So that shows that f is continuous. So unless the convergence is uniform, you are not in a position to fix on a n1 and carry out through this. Okay. So we find that under uniform convergence, the sequence of continuous functions do converge to a continuous function. Okay, prove this. Now you can show that. See, in fact, what happens is that suppose there are all sorts of theorems like if Fn is a sequence of bounded continuous functions on the interval 0, 1, and if it converges uniformly on the interval 0, 1, the Riemann integral of the integrable the functions Fn converge to the Riemann integral of the limiting function f. There the interchange of pieces can be true. So uniform convergence will certainly help you to migrate through this problem to some extent. And there are in all these contexts quite often uniform convergence, the strengthening of the convergence will make you a way. But it's not necessarily always true, because when it comes to differentiability and so on, there may be difficulties. You may have to strengthen that more of convergence. Okay, I think that's enough for the day. Thank you very much. So I conclude my lecture giving a glimpse of the concept of uniform convergence, which is extremely important in analysis. Thank you very much.